In this video we're going to look at graphs of derived functions, and this is the last in the series of videos at the moment on differentiation. Now, before we look at the graphs, just want to go through a few observations, I suppose, that we should have picked up so far from throughout the topic of differentiation. So say we have f of x being equal to x squared, then we should know now that f dashed of x is equal to 2x. So if we actually think about that, if f of x is a quadratic, it's a parabola, x squared, then f dashed of x is a straight line. So that just gets us starting to think about the graphs here. Say f of x was x cubed, then f dashed of x is 3x squared. So that means if f of x is a cubic function, i.e. it's got two stationary points, it then becomes a quadratic when it's differentiated. So it's only got one stationary point. Again, we'll continue the pattern. If f of x is x to the 4, then f dashed of x is 4x cubed, i.e. if f of x is a quartic, that means it's got three stationary points, then f dashed of x is a cubic, it's only got two stationary points. So hopefully you can see the pattern here. So it's useful to know that when you're asked to sketch the graph of a derived function. So what is it you're given, and what is it you're kind of looking for it to look like when you draw the graph of the derivative. Let's have a wee quick look at a graph here, f of x. You'll have seen this graph before, I've used it in a few slides. And we can actually sketch f dashed of x by examining the features of f of x and their gradients. So let's have a wee look at the features of f of x here, and I'll be able to tell you what that means for the graph of the derivative. So we can see here we've got areas where the graph is increasing. And when the graph is increasing on f of x, that means that the gradient, f dashed of x, is positive. So when we draw the graph of the derivative, this area here from negative infinity up to this turning point, that will be above the x-axis. So it'll be positive. Now, we've also got an area here which is decreasing. So in f of x, if we have something that's decreasing, that means that the gradient, f dashed of x, is negative. And when we sketch the graph of the derivative, that area, that interval, will occur below the x-axis because it's negative. Now we've got turning points here as well, and we know that turning points have gradient 0. And if it's got gradient 0, then those points there will actually become roots. Now I know in this example there's already a root there, that's fine, it'll still be a root. And the one thing that I've not addressed so far, and in this diagram actually, is points of inflection. So points of inflection have gradient 0, so they do become roots, but they also become turning points. So it's a turning point sitting on the x-axis. So let's go on. We're going to look at 3 examples with different features so that you can get a good handle on what's happening here. So the first one, shown is a graph of f of x, sketch f dashed of x. So I'm just going to examine this graph more closely. I have a turning point here, -1, -11. And like I've said already, turning points on the graphs of f of x become roots when we sketch f dashed of x. And that's because the gradient of a turning point is 0. So that becomes a root, and you can see here that's become -1, 0. Now, from the beginning of this graph up until the line where x equals -1, the graph is decreasing. So that means that it's got a negative gradient, and on the graph of the derivative we are going to see something below the x-axis. Now after the turning point, here we can see that the graph is increasing, and that means that the gradient is positive, and therefore on the graph of the derivative we'll see something above the x-axis. Now you can see firstly that on the graph of f of x we have a quadratic. We have one turning point, which means in the graph of the derivative we're going to have no turning points. We're actually going to have a straight line. And the straight line is going to come through this area and then through this area here. So it's going to look something like this. Now don't worry about the angle of that because you don't have any other points, and you just need to make sure that you label it as well. So as long as you've addressed the fact that there's a root there, -1, 0, you'll get the marks. So let's have a look at a second example. So again, shown as a graph of f of x, which you can hopefully see this time as a cubic function. It has two stationary points, and we are asked to sketch the graph of f dashed of x. So if we firstly have a look at these two stationary points, remember stationary points have gradient 0, so in the graph of the derivative those become roots. So we have the points here 0, 0 and 3, 0. So we put those down and we label them, and then we're going to examine the behaviour on the original graph f of x up to the turning points and between the turning points and after the turning points. So up to the first turning point we can see the graph is increasing, has a positive gradient, and therefore on the graph of the derivative we will see something happening above the x-axis. Between the two turning points here we can see that the graph is decreasing. So on the graph of the derivative we will see something happening below the x-axis because the gradient is going to be negative. And after the turning point, 3, -18, you can see the graph is increasing again, and the gradient will then therefore be positive, which means on the graph of the derivative we will see something happening above the x-axis. Now on the original graph I said it was a cubic, meaning it has two stationary points here, two turning points. So when we sketch the graph of the derivative we will only have one stationary point. So we're expecting to be able to draw a parabola here, and you can see the areas of the Cartesian grid that's going to go through. So we're going to have something that looks a bit like that, and we can label our graph as well. Again, if you pause the video and you can take this one down in your notes. And finally folks, we'll have a look at example 3. So shown is a graph of f of x, and we want to sketch f dashed of x. And hopefully you'll notice this time that we have a point of inflection. So there's something different going on here from what happened in the previous two examples. So again, we will have a look at what's going on here. So we've got two stationary points. We've got a point of inflection at 0, 5, and we've got a point here 1.5, 8.375. So those are stationary points. That means they both have gradient 0, so they become roots. But what we should also notice is that the point of inflection 0, 5, that becomes a root, yes, but it also becomes a turning point. So we need to be aware of that when we go to sketch the graph of the derivative. Now, examining the behaviour up to the point of inflection, the graph is increasing, but you'll notice it's still increasing after 0, 5 as well, which means that the gradient is positive all the way up to the second stationary point. So the gradient is positive, which means on the graph of the derivative we'll see something happening above the x-axis. Now after the second stationary point here, we can see the graph is decreasing, and that means it's got a negative gradient, and therefore something will happen below the x-axis. Now we need to bear in mind here that we have a stationary point, a turning point, a stationary point on the axis at 0, 0. So obviously if we were to draw a maximum here at 0, 0, that wouldn't work, because we know that we need to draw within this pink area that we've shaded in. So we need to have a minimum here, and then we'll see the curve coming back down, and it will go through the point 1.50 and down into this shaded area here. So we will have a cubic. We started off with a quartic, and we now have a cubic with two stationary points. And just finally, folks, we previously talked about the derivatives of sin x and cos x, and at the time I said to you I would come back and explain this, but I told you at the time that if f of x was sin x, then f dashed of x would be equal to cos x. Now let's maybe look at why that is. So f of x is equal to sin x, that's the graph in red here, and if I just put the turning points on here, that's when x is 90 and 270. So between 0 and 90, the graph is increasing, which means on the graph of the derivative, something will be happening above the x-axis. Between 90 and 270, the graph is decreasing, which will correspond to something happening below the x-axis. And finally, after 270, the graph is increasing again, so that will happen above the x-axis. And you can see there where the graph of cos x occurs. We've got our turning points, which were 91 and 270 negative 1, those became roots as well. And finally, if we look at the graph of cos x in red here, we've got our turning points firstly. So between 0 and 180, the graph is decreasing, which corresponds to something happening below the x-axis in the graph of the derivative. And between 180 and 360, the graph is increasing, which means something happens above the x-axis on the graph of the derivative. Our stationary points became roots, so you can see that here at 0, 180 and 360. And you can see there that we've got the graph of negative sin x in orange here. It's good for you to know where that comes from as well.